Extra strong
Roman concrete.
fully hydraulic
Structural
molded connections.
It's the
Structural engineering
podcast.
Hey everybody, this is the Structural Engineering Podcast, and this is Max doing a quick introduction. This week, Zach and I talked to the President and CEO of Lifespan Technologies. They're a structural monitoring company. Mr. Vanderzee holds 2 engineering degrees, a Bachelor of Science in Mechanical Engineering and a Master of Engineering in Industrial Engineering from Texas A&M University. Mr. Vanderzee started his working career as a production engineer at the U.S. Army Electronics Command. He held a variety of management positions over the next 10 years, including oil trading, project management, and corporate strategic planning. He's been the CEO of multiple companies and for some time worked in business consulting. Lifespan Technologies, the company we're going to talk about now, was originally his client as an advisee, but after a year, they came back and asked if he would lead the firm as it launched into commercialization. He's been with them for over 16 years now. He's currently one of the 25 worldwide members of the Transportation Research Board's Bridge Management Committee and is developing a technology guidance document for practitioners. Mr. Vanderzee is also consulted for the Long-Term Bridge Performance Program administered by the FHA. He's been interviewed on CBS and Fox News, and now finally the Structural Engineering Podcast, and has been published in innumerable magazines, including Bridges Magazine and Engineering News Record. So without further ado, here's our conversation with Peter Vanderzee.
We're really excited to be talking to you, especially on structural monitoring. This is something that I am just super excited about, and I think there's not a lot of great resources, especially for people coming out of school. I know I didn't have the opportunity to learn very much in a classroom setting about this, so we appreciate you talking to us.
Happy to do it, guys. Having been a young engineer myself many years ago, I was always interested in a lot of things that I wasn't doing on a day-to-day basis. I've been fortunate in my career to have a lot of different types of jobs in different industries, and every time there's always a technical component to most jobs, and it's always been interesting to learn. So
absolutely,
I'm on your side on that one. And,
we appreciate that.
I know where you're coming from.
Well, let's get into some questions. So you've been in the construction and technology field for a pretty long time. I know you started your career in the U.S. Army Electronics Command. Could you tell us, from your perspective, how and when did the structural monitoring business get started?
Sure. There's no definitive story that you can come up with about this, but I've been around long enough to know that I have this vision of several professors in a room with a whiteboard and starting to ask each other questions about maybe a recent earthquake event in California, for example. And they said, how could we possibly understand the condition of civil structures after an earthquake without having to dispatch inspectors to do a visual inspection? Is there a way that we could possibly do these kind of things? And I would suggest to you that happened maybe 20 to 25 years ago.
Really?
And the whiteboard got filled up pretty well, and they started to put together what today we know as the Internet of Things. They had sensors, and then they had digital communication technology, and of course the storage of the data in a data center, and then availability over the internet. That all started to come together. And
what were those first sensors? I mean, did they look like? I imagine they were pretty rudimentary compared to today.
Oh yeah, without a doubt. I mean, sensors have improved dramatically over the years. But when these professors really got rolling, they were really supporting PhD students.
Mm-hmm.
And where a lot of the research was going and the money was going into this. And consequently, the business started out with a heavy emphasis on data. The more data, the better was the watchword of the day. And that resulted in some problems in getting this business commercialized, because people were paying too much for it, getting overloaded with data. And it made the analysis much more difficult and then more expensive. So we have those of us who have been very commercial in this business for the years have honed down the data requirements dramatically. There's still a lot of research going on, still a lot of data flowing, but from a commercial standpoint, the data stream now is much less intense.
Interesting. And it's very interesting that, pushing for a lot of data early on was kind of the way when it was especially hard to capture so much data then and store it inexpensive,
That's absolutely right.
Yeah.
So all these things are getting developed, and you're getting all this data, and the next kind of the process is to bring this to the industry and really start using it on a commercial level. So when you're looking at bridges and things like that, how did the State Department of Transportation react to the ideas of monitoring bridges?
Well, that's where where the rubber met the road, if I could use that expression. It's one thing to develop a technology in a laboratory. It's another thing to translate it into commercial use. And those people who were involved, us included, early on, and I'd say 15 or more years ago, looked to the DOTs to commercialize this technology because they're the ones that had all the bridges. There were 600,000 bridges in the country. So given that I was one of the pioneers in the business and I was knocking on doors and visiting state DOTs, I can tell you that when you made a presentation and you looked at the faces of the DOT engineers who were in the room, it was almost like I was selling synthetic blood. And, they looked at you like, why would I want to do this? And I'm asking them, I want you to be the first one to try this, okay?
Oh, it's a tough sell.
You don't mind if we drain all your blood out and put synthetic blood in. Is that okay with you guys? So, more often than not, that's the kind of looks I got. And, then they said, well, that sounds interesting. The second time you go in, well, that sounds interesting, but why don't you come back after you've tried it in 49 other states?
That's a hard thing to fight.
This is not what you call early adopters.
Yeah.
And then, of course, the third excuse was, well, we don't have any budget.
Yeah.
For this. Well, no kidding. It's a brand new technology. Of course you don't have budget. The state DOTs, anytime you're dealing with a governmental agency, they're process-oriented rather than results-oriented. Mm-hmm. So they don't have a lot of money sitting around to try this and try that and so forth. So it was a very difficult sale the first few years. But it improved, and it's continuing to improve. And the more people that are using it, the more accepted it becomes and the more commercially viable it is.
Was there, a switch in perception, or was it a gradual just, getting more information to people and sort of convincing, I guess?
No, I think it was gradual. There was no, magic bullet. There was no aha moment, unfortunately. But, it was just a lot of hard work. It was a lot of driving, airplane flights, hotel rooms, knocking on doors, trying to do your best to provide a reason for these bridge owners to utilize the technology. And, many of them have now come around. About half of the state DOTs in the United States are now familiar with the technology and have used it on one or more bridges.
Are private entities a little more likely to bite on this? I mean, maybe more return for them or easier to get into practice?
Well, yes and no. I mean, that's a great question, but it's a hard thing to answer. When you say private, we did a job for Walmart early in our corporate life. They built a store on Waikiki Beach in Hawaii, and on the second floor, it was a two-story building, and the first floor had the regular Walmart. The second floor had Sam's Club. Well, they got 90% done with construction, and they found out that the second floor beams were not sized for point loads. Okay, so they called us and said, "Oh my gosh, we're gonna kill our shoppers. If we overload beams. Can you put a system in to monitor this for us?" And 6 weeks later, right after Christmas, one year we had 40 sensors monitoring strain values on the second floor beams, and things have worked out fine for them. But yeah,
Wow.
and then we go to the railroads or another private entity that are using this. Very difficult industry to get into.
Really? Because they have some of the oldest bridges, from my understanding. I mean, looking at an average age standpoint.
No, they absolutely do have the oldest bridges. There's about 75,000 to 100,000 railroad bridges in the United States, and they are, on average, the older ones. They're typically corroded, the steel, when they're 70 or 80 years old on average.
Yeah.
That's what you would expect, and they get a lot of heavy use and abuse.
Totally.
But the railroads think differently than the state DOTs. And so you have to recognize that there's a difference in selling to a railroad than there is in selling to a DOT.
Mm-hmm.
Absolutely. Now, kind of going back to the DOT a little bit, was there any state at the beginning that was overly excited about this, or that were kind of jumped into it, a little more quickly than other states?
Well, from our perspective and our history, yes. The answer is South Carolina DOT.
Huh.
And I think most people, would say, well, the progressive states of California, New York, Massachusetts, they would be the first ones to use this, and sleepy old South Carolina is probably the 40th state to try it. Well, that's not the way it worked out.
Yeah,
we found a champion in South Carolina, and he liked what we had to say, and we did a lot of work for them over the last 10 years. So, no, they're still. I would still say they're the leading state in the country for deployment of structural monitoring systems.
Wow,
that's very cool. Yeah, I totally expected California, New York. Absolutely. So that's some cool insight right there.
Yeah. So moving forward in the future a little bit, looking at the sensors we have available. So there are a lot of sensor options out there, which we'll get into later, but it could be temperature, strain, acceleration. What structural elements of a bridge and in what way are most beneficial for structural monitoring?
Well, there's three major components of a bridge: a deck, a superstructure, and a substructure. And of course, a deck, you either plug up the cracks in the riding surface, or you don't, or you replace the deck. That's sort of a binary problem. Either it's okay the way it is, or you replace it. The superstructure is the component that we focus on most, and some of the conditions that lead to the need for monitoring include section loss, cracking. It could be in steel or concrete. Unusual displacements where various members have separated, out of plane bending. These are all symptoms, if you will, of structural distress.
Yeah.
The substructure is a different kind of an animal in the sense that, critically important, of course, the whole bridge is founded on the substructure, but it has sort of a different failure mechanism. The superstructure is more, let me just go back and say, the substructure is more catastrophic in failure, more brittle, of a brittle failure mode. It's either okay or it fails brittly and very quickly. The superstructure is more ductile in its failure modes. Things start to appear, they kind of get worse, and they get worse over time. And then that really makes for an ideal structural monitoring candidate, the superstructure, where you'll have more of a ductile failure mode over time, so you can watch it carefully and you can keep a good close eye on any deterioration that's happening.
Interesting. That makes sense. And I imagine when you're looking at bridge failures, a substructure bridge failure would be something like from scour or an extreme event, that might be more rapid. And then, like you're saying, over time you get degradation of the main bridge structure. Yeah,
I'll make this point. The most common cause of bridge failure in the United States is scour, is a substructure problem.
Yeah,
we lose more bridges from that reason than the superstructure. And that's understandable when you consider what you just noted, that the failure mechanism tends to be brittle. In other words, very quick. When the substructure is undermined, it can fail in a second, and without any prior warning.
Interesting. Yeah, so there's really nothing you can do. I mean, from a monitoring standpoint, I guess I want to ask, if someone is concerned about scour on a bridge, but understands that, the monitoring equipment isn't perfect for that, is there something that can be provided, though, that gives them some level of confidence? Does anything change that can be monitored?
Yes, there is. And there's really two ways to do this. You could use what do they call those? Total stations, if you will, or LiDAR technology that can watch movement of the substructure, the piers or the bents. Or you can use inclinometers. We've used those on a number of occasions. And when the substructure is starting to move, an inclinometer will give you very good, very accurate readings as to movement. And when the movement is minimal, I mean way less than 1 degree, and over a longer period of time, you generally have a lot of time to react to that.
Absolutely.
There are times when you have an emergency situation and the bridge can fail very quickly.
So how many different types of sensors can be used for structural monitoring?
Well, there's a number of what I would call go-to sensing devices that are probably used 90% of the time or more. Let me list those out for you. Displacement sensors. The sensor we use most often is fundamentally a displacement sensor. It measures movement between two fixed points, and of course that can be translated back to strain. So displacement, strain, temperature, acoustic, or inclinometers. I would say those 5 technologies right there, and it's hard to even call them technologies, let's just call them sensors, is probably over 90% of the sensing devices that are used for structural monitoring. The real important point of this is not the type of sensor, it's whether that sensor generates actionable information.
Definitely.
When you're a PhD student and you need data, and you need a lot of data, you're not going to take any actions. You don't own the bridge. Okay, you're doing research. You're trying to figure out, a new equation that explains the world. And that's okay. I get that. That's important. But when you own a bridge and you're responsible for its safety of the users, the whole key in structural monitoring is the generation and analysis of actionable information. What is it telling me? What can I do with it? And do I need to do something soon? That's the key.
So part of the monitoring services and sensors that you provide, does that come out to be a report that you provide kind of monthly, I guess, for that, what you're stating, that actionable item?
Well, we offer a subscription service for the data, and that service pulls the data off the internet, or through the internet, I should say, from a data center, a secure data center, where all the data is stored. And we can present the data in a number of different ways. We have our common package or normal packages with a graphical presentation of a trend. For example, time being the x-axis and strain being the y-axis. That's pretty straightforward and easy to do. We have the ability in that package to download all the data in an Excel spreadsheet. More often than not, and no, I shouldn't say actually all the time, we do not do data interpretation. Okay, we can put the data in a number of different forms and provide it to the owner or the owner's engineer if they're using a third party. But we are not in the interpretation business to take that data and do some really deep analysis with it, come up with recommendations for the owner. We leave that to the people who have, really developed the expertise in that over many, many years.
on here we've got what are the two most important applications for structural monitoring, and if you wouldn't mind elaborating on that. I believe you kind of touched upon it, the superstructure, and the kind of the different elements of the bridge. But if you want to elaborate a little bit more on what you see as the two most important applications.
Okay. What I talk about superstructure and the structure for the components of a bridge. That's where you'd install the sensors, but that's not necessarily what I would call an application. There is two main applications for structural monitoring. The first is what is the structural integrity of the bridge or building or anything else that we're monitoring. We shouldn't try to limit this only to bridges. There are any number of other structures we can monitor. But for the sake of the argument here today and the discussion, we'll talk about bridges. As an owner of a bridge, I am responsible to visually inspect that bridge every other year with a team of generally two people who come out and do what we would have to call a tactile inspection. They put their hands on the structure. They take pictures. They make notes. Sometimes these inspection reports can run 20 to 30 pages long. And this is a requirement by the Federal Highway Administration. Now, 20 years ago, the Federal Highway Administration studied what they call the efficacy or effectiveness of visual inspection. They put out a report that was very interesting for those of us who are in the structural monitoring business. The report concluded that visual inspection is very subjective and highly variable. Now, there used to be a 0 to 9 ranking that you would give all the major components. 9 is like brand new, and 0 is out of service. 4 was structurally deficient. The report the FHWA put out said visual inspection can vary by plus or minus 2 grades.
I've actually read this report, Peter, and this is probably what kicked off my interest in this field is, reading that, even as someone that, I wasn't an engineer yet, this was in school, I was blown away, all the effort put into inspecting bridges every other year, 600,000 plus bridges, and it's not even a very good system, it seemed to me. That blew my mind.
Well, I'm glad you read it. It's a fascinating report. And even though there have been some level of improvements over the years with visual inspection, it's still not very good in terms of pinpointing problems. Mm-hmm. And this is why I advise our customers and future customers that when you have a bridge component, especially the superstructure, that's rated at 5 or below, that's the time to start thinking about using structural monitoring. Because you have to get a detailed, precise, timely understanding of condition, or you're not going to be able to do the right remedial action or replacement effectively for the limited amount of funds you have. Mm-hmm. Visual inspection is intentionally conservative. Okay, when you train inspectors, and one of them says a 4 and the other one says a 5, the 4 is going down on the report.
Yeah.
Okay, so when the press comes out and says, "Oh, woe is me, we have 60,000 structurally deficient bridges in the country. The bridges are crumbling every day," they scare people. Okay.
Yeah.
Well, the number is not 60,000. I think it's closer to 30 or 35.
Mm-hmm.
That's still a big number, but bridges aren't crumbling. Okay, they don't look good. Older they lose their appeal visually, mm-hmm. but right. They carry the load. Okay, and if you have limited funding as an owner, you're going to want to apply that funding the most effective way possible. And the only way you can do that is when you really understand the condition.
Yeah.
And more often than not, when we do monitoring, we're finding bridges to be in much better structural condition than visual inspection would indicate. This is a major problem across the United States. It's called postings or load ratings.
Yes, yeah.
Where a bridge, there's a sign at the end of the bridge that says load limit 10 tons. Now, that sounds like a good thing, and when you drive your car across there, you probably say a prayer and say, thank you for somebody's watching this and limiting traffic. But what you fail to see, because you don't go over it enough, is a truck that weighs 40 tons that's going over the bridge right before you.
Yeah.
Okay? Nobody obeys these postings. Nobody. And there's never any enforcement that you'll ever find. Ever see at all. So you've got to ask yourself, well, there's two types of users, heavy users of these bridges, the law abiders and the law breakers. The law abiders are the companies like Walmart and Target and, big truckers that don't want to get caught with their truck at the bottom of a ravine in a collapsed bridge. Okay, that's not good publicity for them. So they'll take the detours. Then you have the law breakers. Well, they typically go over 3 o'clock in the morning, so they can't ever get caught.
Yeah.
More often than not, logging trucks and farm vehicles.
Yeah.
Many farmers in rural areas completely disregard load postings. So one of the more effective applications we have in this business is to use sensors to determine the load capacity of a bridge. And more often than not, and the last 50 that we've done, last 50 bridges, 40 of them did not need load posting.
Really? Wow.
That's very important, 80%.
Yeah, that's a huge difference. You mentioned before the Sam's Club. Can I ask what other structures do you think can benefit from the use of structural monitoring solutions?
Well, certainly buildings. So I've heard some talk recently about installing sensing devices in buildings to make sure there's no undue movement. These would be primarily displacement sensors or strain sensors, so you can validate the design parameters and so forth. Parking decks are a very good market for this because, they tend to be Lincoln log kind of, put together precast elements, and they move.
Yeah.
As the temperature changes, the traffic changes, the loading changes. Monuments, we years ago, even before my involvement, the company did a monitoring project on the Washington Monument in Washington, D.C. They had cracks in the facade, and the Park Service was trying to figure out, why are we getting cracks in the facade? So we were doing that one. We've done a stadium, wind turbines, offshore platforms, pipeline. But, anything of that nature where you have movement or degradation of a structure, structural monitoring allows you to keep an eye on it and to be very objective in terms of its current condition and its deteriorating condition over time.
So there are a lot of options out there.
Yeah, we've been seeing quite a bit of monitoring kind of going into the world of high seismic for large structures, and there's some companies coming out with some items that kind of help provide post disaster, post seismic event analysis to determine what the building actually went through. So I've seen lots of
core brace, right? They now have an on brace strain sensor. And we're talking to them in 2 weeks, I think. So definitely interested to see what they're doing there.
If I can go back to where we started this conversation, where the professors were on the whiteboard, that's exactly what they were thinking about. How do we determine the condition of the structure post-seismic activity?
Yeah.
Is there a way for us to know that building is way worse than the building down the street, and we should send our inspectors to the first building, which is more of a risk than the second building?
Absolutely. I mean, that makes, I think, the most sense from a life safety standpoint. Was that the direction it went at first? It seems like not, but, I'm not in the field. Is there a big push there still?
Safety sort of a come-along thing for everybody. It comes with the process of understanding condition. If you understand condition in a more objective and precise manner, then safety is naturally enhanced.
Yeah.
There really aren't many people, many owners of bridges who will put a monitoring system up solely for the purposes of enhancing safety. I think what the owners would tell you that if they have the slightest inkling that there's a safety problem on a structure, it would close and they would replace it.
Yep.
So, again, that's a come-along feature, a come-along benefit, if you will, but it is an important benefit.
Yeah. Okay.
Yeah. So with that said, kind of going back to the, our young engineers, kind of our audience, kind of the challenges and opportunities. Let's say, Max or I or someone that's in school right now wants to get into this industry of structural monitoring.
Well, I think there's several things you have to keep in mind, and you have to accept the fact that when you graduate from college or even graduate school and you've taken several courses in this, you're nowhere near being an expert. Okay? It takes many, many years. Let me explain what I mean. The biggest single scope, if you will, for an engineer in terms of using data generated by structural monitoring is the determination of structural integrity. Okay? The ability to look at the data and say, that bridge is safe to use, knowing that even if it was posted, you're still going to get heavy loads that are going over it.
Mm-hmm.
It's not an easy thing to know. And as you go on in a career and you earn your advanced degrees or you get a professional engineer license and so forth, the people who are really, really good at this probably have a minimum of 25 years of experience.
Wow.
One of the fellows that I work with, who I think is one of the best structural engineers in the country, for bridges in particular, has got 40 years of experience. He can look at data and say, that bridge is fine. It's usable. And then he can put a report out, sign his name to it, stamp it with his PE stamp. And that's the kind of thing where some of your young engineers who are listening to this, should probably be headed. I mean, that's a very, very important part of this business.
Mm-hmm.
And, again, the idea of gaining experience will give you enormous amount of confidence over time.
Yeah.
Because you've seen a lot of unusual things. If I told you that there is a major bridge in New York City that you can put your hand through the webs of floor beams in many spots, you would probably be aghast. You'd say, they have to close that bridge. That's terrible. Well, we've monitored that bridge. I know about that bridge. I've been over that bridge. Okay?
Mm-hmm.
There are many, many areas on floor beams where the salt that they put on during the winter has worked its way down to the steel, and it's corroded the steel completely through. But yet, we have the data collection, and we know that the bridge is still safe to use. Well, what does that do? Well, instead of a $50 million steel replacement program, the owner can then say, well, we'll wait until we see some imminent signs of a problem.
Yeah.
Not a collapse. It's not going to be a collapse of the bridge, but you can see where the degradation is bad enough that you'll have to do something. Well, they've waited now for the better part of 8 or 9 years. Well, if you don't have to spend $50 million for 9 years, you've generated a lot of value.
Yeah, absolutely.
All right, last point I want to make. The most important thing for the young engineers is to keep in mind this concept of actionable information.
Mm-hmm.
The idea here is, in doing this right for owners, is we're not putting on sensors that are going to lead to nice-to-have information.
Mm-hmm.
The owners couldn't care less, okay? Let me give you an example. Corrosion sensors, okay? There were many corrosion sensors that were put in the new I-35W bridge that collapsed in Minnesota in 2007. My opinion of that is, if you can watch corrosion that's embedded in corrosion of rebar that's embedded in 12-inch thick concrete, what good is that going to do you? So it's corroding. What are you going to do? Replace the deck?
Yeah.
Because you have 30 areas that have more corrosion than you think. You're never going to do that. That's an example of nice to have, but not worth the money. and
Yeah.
it's not actionable information.
Okay.
So with kind of all that said, you're talking about, really a lot of these could, potentially be life safety, but you're saying, once you monitor it and it's not really a big issue. For a monitoring company, where does the liability stand with this data?
Well, that's a very good question, and I'm going to try to answer that in a very simple way. We're a data provider. Okay, that's what we built our business on. We do not interpret the data. So what would that tell you? Where is our liability lie? Well, our liability lies in the reliability of the data stream.
Yeah.
If we were supplying a system that was only half effective, when we said we would have data like every minute, we would have a data point, and half the time the system was down, that's highly unreliable, and we generate a lot of liability doing that. So you would expect that. So we focus in our business on exceedingly high reliability data streams so that we have essentially no liability. There's never a point where we lose data. Let me give you an example. We monitored a bridge that was on the Outer Banks of North Carolina for over 2 years. That bridge experienced 3 or 4 hurricanes during that time and two major winter storms. I'm talking about winds well in excess of 100 miles an hour, high seas, and this bridge was right on the coast.
So high salt, a rough environment.
And we were sending the data via the cell network and a modem to our data storage center, and running the system off of a battery with a solar backup to recharge the battery. In 2 years, we never once lost a data point.
Wow.
All through 3 or 4 hurricanes, and I'm talking about hurricanes where the eye of the storm came very near the bridge.
Wow.
So that's what I mean when I say ultra high reliability, and that's one of our
not go down.
Of our company. That's what I mean.
So then you're also using the most reliable sensors that, your whole system is overly reliable then as well. So that's pretty cool.
Correct.
That's great. Where would you say young engineers should plug into the data analysis process, and where not?
Well, let me start off by doubling back to this whole idea of where are the opportunities and what do you need to do. The first thing a young engineer should get up to understand is, when you're looking at a plot of strain versus time, what's acceptable strain and what's not acceptable. 100 microstrain is practically meaningless. 300 microstrain starts to get your attention because that's about 1 KSI of stress in say, steel. Is 500 microstrain too much? Well, not really. You're not anywhere near the yield point of the steel, but there are times when you might go up to, 1,000 microstrain. And what would happen if you have stress reversals? These are all things the young engineers have to learn. They have to understand what can happen in a structure. It's one thing to design a bridge and to understand how the various members are put together, and you put bolts in. We're not welding anymore. We're bolting. And, everybody assumes that, the load paths are all, as the design indicates. Well, nothing could be further from the truth. Once a bridge is built, it starts to settle out, if I can use that term. I don't mean necessarily down in like the foundation, but it moves around and it's finding its lowest point of potential energy. Okay? It's trying to find the spot where it can breathe and go, now I'm comfortable. Everything's fine. Okay? So, some members that you thought were in tension might be in compression and vice versa. And those are the kind of things that, as a student or a young engineer, you really don't understand that until you've seen it. And then you ask questions of the more experienced people you're working with. Why did that happen? What caused that? One of the things that we found over the years is that delta T, temperature differences, have an enormous impact on observed strain values. Up to almost 80% of the strain values we pull off of structures can be attributed to different temperature.
Yeah.
Now,
Jeez.
so if you had a sensor out there and it was reading, 700 microstrain, and I could prove to you with statistical analysis that 80% of that was temperature driven. Well, now all of a sudden you're going, okay, let's see, that's 560 microstrain for temperature. I have no control over that whatsoever.
Mm-hmm.
But the remainder, 140 microstrain, is due to live load.
Mm-hmm.
Should I worry about that? No.
Yeah, now it sounds a lot smaller.
Live load, that's nothing.
Yeah.
Okay? So that's the type of thing that I mean when, a young engineer gets involved in these things and starts to learn these. I'd almost call them, these are aha moments. Wow, I didn't even think of that you could have stress reversals, or temperature really makes that much difference, or the load paths are completely different than what I expected. That's what happens to structures as they age. Things change, just like the human body changes. Structures do the same.
Interesting. Yeah, that's something I don't think I would think of a stress reversal. I don't think that would occur to me. I picture a building often in the way that we design it, and load path just follows the form that you give it. But I certainly believe it.
Yeah. So now that we've kind of gone over structural monitoring, young engineers, how, your experience with it, where would you say that the current state of structural monitoring is today?
Let me give you 3 conclusions, if I can, on to answer that question. All of the companies that are involved in this, ours and some of our competitors, we're continuing to penetrate the market. The market is still very young. I've seen reports that suggest this business is going to grow at somewhere between 15 to 20% per year over the next 5 years. That's really substantial. So we have a long way to go yet. We have a long runway. There's plenty of opportunities. That's a good piece of information for young engineers.
Yeah.
Secondly, the young engineers need to understand that for a customer who wants to buy these solutions and systems, return on investment is critical. We are not in the business of doing research. We're in the business of, when a customer gives us $1, we want to give them $3 in value back.
Yeah.
That's the way you maintain customers. They come back for repeat business, and you keep them very happy. Return on investment, very, very important. And that's becoming more and more important over time.
Yeah.
The third thing is, and this is just interesting to me and maybe to your listeners too, the academic side of the business, the PhDs, if you will, the folks who are striving to get that final degree, they're still trying to capture commercial work by going to owners like state DOTs and railroads and saying, we have the best thing possible. We just developed this last week. You ought to give us $1 million. We could put it on your bridge in a half an hour. The owners are a lot smarter than that. They're moving away from the academic approaches almost completely now, and we're really into commercial business today. And like I say, that all revolves around the return on investment. And to the extent that any of your young listeners are going to go into businesses where, they try to earn a profit every year, you have to deliver an ROI to your customer.
Yeah, that's exciting. So it's on the up and up. I think one day, I've got a lot to do in structural engineering yet, but in 10 years, I want to have a toe in structural monitoring. I just think it's so cool, but I'm busy with the design side for a little while.
Well, that's where you start. I mean,
Yeah.
you need to start there. You need to understand how the equations are driving you to build something. But when you do structural monitoring, then you find out, well, those equations were simplifications to the first step. And you know what? The contractor didn't build it quite like I thought he would. And, the loads are different. The loads are different, and the deterioration rate affects it. And the temperature is more of an important issue than I ever thought. Wow, there's a lot to this.
Yeah. Well, we don't want to take up any more of your time than we deserve, but we got one more question for you, and it's one we like to ask all of our guests. And that is if you could, give our listeners a couple of nuggets of wisdom, 2 to 3, from your 16 plus years of experience in this business. What have you taken away?
I think some very important nuggets. Let me give you 3. Number 1, do not, and I mean do not, overstep your expertise.
Yeah.
There are very few 24-year-olds who have structural engineering master's degrees who can look at a data stream from a complex bridge and tell anybody what's going on. Not going to happen. So don't ever go to a meeting and say, I know everything that there is to know about structural monitoring and how that bridge. No, you don't.
It says right here, I'm a master. It's got it on the piece of paper.
Sorry, piece of paper. That experience is much more important. So don't overstep. Number 1 nugget is don't overstep your expertise.
Yeah.
Number 2, ask questions. Keep asking questions. Why is that that way? I never expected this. Explain this to me. You should be asking those questions, young engineers, of the guys that have 30 and 40 years experience. And if you don't ask questions, you're not going to learn. And so, find a mentor that you can work with. If you're really interested in structural monitoring, find somebody that's done 10 bridges or more that really understands the nuances of a structure and what can happen, and ask questions. Keep asking them. Make yourself obnoxious. It's the only way to really learn. Okay? And the 3rd nugget I'll leave you with is never be afraid to say, I don't know. Okay? All of us that went through an engineering curriculum, when we graduated, we thought we were God's gift to structural engineering. Sorry, not happening. Okay? Really up until the time when maybe you got your PE, or even 5 years after, I don't know what to be the first question that comes out, or first statement that comes out of your mouth, because there are many, many different things that can happen to a structure, and given the fact that on a bridge you've got 3 major components, they all interact with each other in different ways. They have exterior forces that act on them, whether it's live load, temperature, scour. It's a complex business. There are no easy answers, but the more you get engaged in this, the smarter you get, the more valuable you will become to yourself and to the company you work for, but especially to the owners who need this kind of information.
Yeah. That's awesome. Thank you so much, Peter.
Thanks for the opportunity to be with you guys, and I hope you get a lot of listeners to this podcast. And if you ever want to do it again and amplify, you just let me know.
Thanks, everybody. That's it for this one. If you'd like to learn a little bit more about Peter, you can check him out, lifespantechnologies.com. If you enjoyed this podcast, please subscribe or share it with a friend. If you didn't enjoy the podcast, maybe you could share it with someone you don't like. That would be fine, too. All right. Have a great day.